So this is the review for the final exam, and try to write as much as possible. Try to get that. This is where the questions are taken from, the topics that I'm going to talk to you about quickly. And after every topic, I'll stop to see if you have questions, and then we'll roll on like that. First topic is capacitors. Capacitors are used to store charge or store energy. And the basic definition of a capacitance is it's the ratio of the charge to the voltage. So usually there's a question, if the charge on a capacitor is doubled, what happens to its capacitance? Students are prompt to thinking, if you are too mathematical, you look at this formula and say, oh, if the charge is doubled, the capacitance gets doubled, which is wrong. Because when the charge gets doubled, the voltage also gets doubled. Therefore, the capacitance is a constant. Even otherwise, capacitance depends on the geometric features as given by this formula. Capacitance depends on the area of the plates and the distance between the plates, also on the dielectric between the plates. So keep that in mind. So as you're preparing on each of these topics, remember that this is not mathematical. You have to really go deep down into this. Capacitance is measured in farads, charge is in coulombs, and farad is nothing but coulomb per volt. K is the dielectric constant, and it shows how many times the permittivity is above that of air. Of course, that is the permittivity of free space. Constants will be given to you, but just know epsilon naught is the permittivity of free space. Capacitors can be combined in two ways at least. And when anything is combined in series, in this case, charge is the same, right? And if you combine them in parallel, then what is the same? The voltage stays the same. That's right. So when capacitors are in series, you get 1 over C is 1 over C1 plus 1 over C2, but in parallel, you just add them. Now, like I said, a capacitor is 1/2 CV squared, but you can substitute for the terms and get it in two other different formats. So there are three ways to calculate the energy of a capacitor given by these three formulas. So as an example, I could ask you a question like this. What happens to the energy of a capacitor when the voltage on it is doubled? And then you'll have to look at, okay, which one am I going to use to answer? You see, obviously this is the one you're going to use because you know that C is a constant. So now you only need to look at, oh, the voltage is doubled and there's a square there, so the energy is going to be quadrupled. So you got to look at which one to use and answer the questions. Next up, electric field. Electric field is defined as voltage by the distance. That's when you have two parallel plates. That's how you have the electric field between the plates. And electric field can also be defined as sigma by epsilon naught, where sigma is the surface density of charge. Now, what do you mean by surface density of charge? It is the charge divided by the area. Surface density of charge, or simply surface charge. Now, that's going to be in coulomb per meter squared, although I've not written it. And this is the field. Remember, this is the field due to a single plate. No, actually, it's between two plates. Sorry, it's the field between two plates. If it's a single plate, does anybody know what will happen? It'll be sigma by 2 epsilon naught. It'll be half of that. So if it's a single plate, this is two plates. Resistance. Resistance of a conductor depends on its length and on its area of cross-section, given by this formula. A is the area of cross-section, therefore it could be pi r squared, because usually it's a circular cross-section. Rho is a constant called resistivity or specific resistance, and the unit is ohm meter. And when you combine resistances, you know that the formula is exactly the opposite of that for capacitors. So when you combine them in series, you just add, but in parallel, it's 1 over R is equal to 1 over R1 plus 1 over R2 plus, and so on. Now, this is where I've asked questions like, if you stretch a conductor to twice its original length, what happens to its resistivity? It remains the same, because resistivity depends on the material, right? So you got to be careful. Once again, I'm telling you, don't be mathematical alone. You have to think. So just don't go, hey, I have all the formulas, I'm going to get everything. No, you're going to be tricked. So if you only look at the formula and you're not thinking, you will say, oh, the length is doubled, the resistivity should become half or something like that. But resistivity is a constant. On the other hand, if I go back to the same question and ask you, if the length is doubled, what happens to the resistance? So, I mean, a conductor is stretched to double its original length. A conductor is stretched. A conductor, I mean, is stretched to double its original length. So what happens to its resistance? So once again, you made a mistake there. Because when the length is doubled, the area of cross-section will become half. So that will double the resistance. This will also double the resistance. So the resistance becomes 4 times. The molecular model of electric current, where we talk about drift velocity and all that. The current flowing through a conductor is given by I is equal to NA VDQ. Where, do you know what N is? Well, you could guess it's a number, but be specific. It's the number of free electrons in 1 meter cube. Number of free electrons in 1 meter cube. A is the area of cross-section. Then you have the drift velocity, which is really small, and Q is the charge of the electron. Current density. Current density is a vector, as opposed to electric current, which is a scalar. Remember that. Electric current is a scalar, but current density is a vector. And current density is defined as I by A. So from that formula, A just gets cancelled out, and you have this as the formula for current density. The unit is going to be ampere per meter squared. And that's a picture just to show you the free electrons and their drift velocity. Next is, how does the resistance change with temperature? Does the resistance of all materials increase with temperature? The answer is no. For conductors, the resistance increases with temperature, but for semiconductors, resistance actually decreases with temperature. And so the formula that's being written is applicable for both. The difference is going to be in the constant alpha. Alpha is positive for conductors, and alpha is negative for semiconductors. And of course, RT is the resistance at T degrees Celsius. R naught is at 20 degrees Celsius, which is the room temperature. And delta T is the change in temperature. Alpha is called the temperature coefficient of resistance. it is negative for semiconductors. So that's why I said alpha may be negative, and that's for semiconductors, but the same formula can be applied. Ohm's law, very important rule. Voltage is the product of current and resistance. Electrical power can be written in many ways, but the basic definition is it's the product of voltage and current, and then you can substitute for voltage and get it this way or in a third way. And this is how it's defined. Energy, that's what I'm looking at here. This represents energy. Electrical energy is integral P dt, because power is dE by dt. So same thing. Power is dE by dt, or E is integral P dt. Internal resistance. Every power source has an internal resistance. A battery has an internal resistance as depicted in this diagram. So if you connect the power source to an external resistor, you have to consider the internal resistance that's inside it if it's given in the problem. And that's always imagined to be connected in series with it. You know, that whole thing is just the battery. And that's the little r is the internal resistance. So the total resistance becomes the sum of the two, and therefore the current would be E by the total resistance. And so we're going to get a voltage across the external resistor, which is going to be defined by I times R, and then you plug in the value of I. And you will understand that you're not going to get the entire EMF of the cell here, right? You're going to have what's called lost volt. So to find the lost volt, you just take E minus the voltage here. That's it. So if this is like 10 volt, you might get 8 volt here, so 2 volts are lost. So that's what you mean by lost volt. So for an ideal battery, the internal resistance must be 0. Right? That's when you will get all its EMF as a voltage. I thought of writing this again. So combination of capacitors and resistance is just a comparison. So I'll quickly run through that because we went through it. I just thought about showing it to you, and because some of you make that mistake still. So look how the formulas are different, right? See that? You've already written that, so yeah, Kirchhoffs Law, 10-point question once again. It's coming up, so you can all answer that and just be careful. There are two laws. One is the junction rule, where the net current is equal to 0, and then the loop rule, where the net voltage drop is equal to 0. I just thought I should remind you about this. So here's a diagram, and according to this diagram is what's the relation between these three? I1 is certainly I2 plus I3, right? I1 is I2 plus I3. And then, depending on which loop I've taken, I can't remember. So I think I've taken I1R1. So in this loop, I1R1 plus I2R2 minus. Why minus? Because you're hitting the negative. See that? So if you're going in the direction of the current, take it as positive. So I1 times R1. And then you continue going in the direction of the current. That's why it's also plus I2R2, right? And then when you come here, you're hitting the negative, so it's minus V1, and then all the way back is equal to 0. Does that make sense? And then again, in this loop, let's try again. So I3, R3, you're going in the direction of the current. What about here? Are you going in the direction of the current here? So the question is, what's the current in this branch? It's I3, right? So yes, so it's I3 R4, and then when you come here, you're hitting the positive, so that's why it's plus V2, as you can see. And then when you come back here, you're going against the current, so it's minus I2 R2 is equal to 0. I hope you understood that. Now, measuring instruments, there are several, but remember that it's a galvanometer that's always converted into an ammeter and a voltmeter, right? So now we've got to look at how a galvanometer is converted into an ammeter and into a voltmeter. So first, if you look at this diagram, you see that whenever you use an ammeter, it's always connected in, how is it connected? In the circuit. Look at this. In series, because you want it to measure the same current that flows through those resistances. Okay, that's number one. An ammeter is always connected in series. And how do you change a galvanometer into an ammeter? By connecting a very small resistance in parallel to it. So that's a galvanometer. The resistance of the galvanometer is G ohms. And then you have a very small resistance connected, which I should have called it RP because it's in parallel, right? I may or I may not change it, I don't know. So just label this as RP because it's connected in parallel with this. And then you have a current coming in, but at this junction, that current splits into two parts. Only a small current can flow through the galvanometer because it's a very sensitive device, isn't it? So Ig is that part of the current that flows through the galvanometer. And the remaining current, what is the remaining current? Isn't it I minus Ig? Because out of I, right? So that's how it's labeled. And then I even forgot to label this current as I minus Ig. Just label this, put an arrow there and label it as I minus Ig. And then when you take the voltage, voltage is either Ig times G or I minus Ig times Rp. So, and then rearrange to make that resistance the subject. That way you can calculate, I changed it to Rp, but I forgot to change it here. So that way you can actually calculate the resistance required to convert a galvanometer into an ammeter. Writing with my fingers. Whenever a voltmeter is used in a circuit, it's always connected in parallel, as you can see, because you need to measure the same voltage. That's a big difference. Voltmeters are always connected in parallel. And how do you convert a galvanometer into a voltmeter? The exact opposite of what you did before. So now you connect a very high resistance in series with the galvanometer. So that's where it's called RS for obvious reasons. And you have that tiny current that comes in through the galvanometer. How do you know that current is going to be small? Because the total resistance of these two is going to be high, isn't it? Because this is a very high resistance. So now the voltage is simply that current multiplied by the sum of the resistances. So Ig, now Ig into that total resistance, and then rearrange this to give that. So that's how you calculate the resistance that is to be connected to convert it into a particular voltmeter. CR circuit. This is also a lab where a capacitor gets charged through a resistance, right? That's the formula for buildup of charge. And then the second one is the formula for discharge. So formula for charging and discharging. And you know what is called time constant? Time constant of this circuit is simply the product of capacitance and resistance. C times R is called the time constant. So learn about the definition of time constant.
First one is charge.
Yep. First one is the charging equation. The second one is the discharge. And what is Qm? Of course, that's the maximum charge. But how do you find that? It is simply capacitance multiplied by the EMF of the cell. Isn't it? Mm-hmm. Because Q is equal to C times V, right? Yeah. So you have to remember that. So that will be something. So that's why I keep saying, if you write an equation, you got to think around it. Got to think, oh, what's that term? How do you find that? You know, what is this? That's the time constant. How is it defined? It's the time taken for the charge to build to 63.2% of its maximum charge. You know what I'm trying to say? So just go around the formula and think about all the terms. And in an LR circuit, you have similar formulas, but instead of charge, it is the current that builds up, the current that grows or decays. And there is a difference, if you can notice. There is a difference, especially in this part, where time constant is now inductance divided by resistance, right? It's not the product, it's L by R. And I specifically wrote, derive the equations. You should know what that may mean. Derive the equations. Know how to get it from scratch, these equations. On to magnetic effect or magnetic force on a current carry. No, it's actually first one, it's a charged particle. Anybody, before I show you the formula, do you know the formula? Magnetic force on a charged particle. Of course, it's moving through a magnetic field. That's where you have the cross product come in, F is equal to Q, V cross B. Remember that? That's where you could use matrices to find. We have had 10-point questions on that, so, and I think you're okay with that. So the force is given by Q, V cross B, and it's given by the right-hand rule. Remember the right-hand rule? So just as a review, what do the fingers represent first when you stretch it? It represents the velocity. But you're talking about a positively charged particle. Positively charged particle. Remember? Yes. If it's a positively charged particle and it's moving that way, you hold the fingers in that direction. And then when you bend it at right angles, it should be the direction of the magnetic field. And then the thumb will give you the direction of the force. So if it's a positively charged particle and it's moving that way, hold your fingers that way, and then the magnetic field, the thumb will give you the force. But if it's a negative charged particle and it's moving that way, then you have to hold the fingers in the opposite direction. You see that? Negative particle moving that way. Because the fingers should show you the direction of current. Just remember it that way. Isn't current always opposite to the flow of negative particles? And in the direction of positive. So that way you can remember the right-hand rule. So we could have a question based on that, and you should not miss that. At that point, it's not calculation, it's just understanding. This is the magnetic force on, I wrote it again. Okay. Oh, I wanted to give you an example. Just the simplest of all examples with that. That's why I wrote that again. Assuming it's a 1 coulomb charge, and isn't that what you do? IJK 340, because there's no K here. And then I took the simplest. I just wanted to make it easy. No I and j here, it's only k. So you end up with that. I hope you understood that. Did you? Okay. I wrote that a third time. I wrote that a third time, but a little different now. Now you know that in this diagram, that represents a magnetic field that's, help me out. What does that show? Into the plane of the paper or into the plane of the board in this case? And you have a negatively charged particle moving this way, clockwise. Negatively charged particle. And so the force acting on it will be inwards. That provides the centripetal force. And you know that centripetal force is given by mass times square of the velocity divided by radius. So you put those two equal to each other. Remember, I'm not teaching you, I'm just reviewing. That's why I'm going fast. We did all this. So the force is now this, and then you can make the radius the subject. And time period, or period, is the time taken for one rotation, which is going to be given by this. And then when you substitute, you finally come to, after all the cancellation and all that, you get 2 pi m by qb. What's really important here is to notice that the period does not depend on the velocity. Did you all hear me? The period does not depend on the velocity. That could be a conceptual question. Because the final equation does not have velocity in it. Neither does it have radius in it. Because they cancel out. Again, you know that frequency is the reciprocal of period, right? So if you're asked to find the frequency, you take the reciprocal of that. So it'll be qb by 2 pi. So next you have magnetic force on a current carrying conductor. Now it's not a charge, current carrying conductor. And then you have another cross product. You have I L cross B, where you have, that's the length of the conductor and that's the strength of the magnetic field. And these diagrams show you the direction of the magnetic field, not showing the force, but showing the direction of the magnetic field due to a current carrying conductor. Biot and Savart's law, that gives the magnetic field due to an elemental conductor, really small conductor, or if you imagine that a conductor is divided into so many small, tiny segments, dB is the magnetic field due to one such segment, and I think I have the diagram, and that's given by this formula, mu naught I dl cross r by r squared. And then if you expand the cross product, you're going to get dl sine theta. Remember, this is just a unit vector, so please don't see in your mind as this getting cancelled with this. Please don't. This is a unit vector. And that's why the cross product becomes dl sine theta and not dl r sine theta. It's dl sine theta. And I've written that specifically there, so you don't make that mistake. So here's the diagram that explains everything. dl is the length of that segment, r is the distance to the point where you want the magnetic field. Theta is the angle shown. I is the current flowing. Okay, the magnetic field due to a straight conductor. Now this is where we used Ampere's law, which I'm going to show you in a second. Magnetic field due to a straight conductor is given by mu naught I by 2 pi r. That's only if it's a straight conductor. And can anybody tell me what the length of that conductor should be to use this formula? Because the length of the conductor is not in the picture there, right? So what should be the length of the conductor? Or can you use this for any conductor of any length? That doesn't make sense. No, it should be infinitely long. This formula can only be applied. That's why I keep saying, just writing the formulas will not do. If it's an infinitely long conductor, that's when you can use this formula. Okay. So now if you have two parallel straight conductors, both infinitely long, the force between them is given by this formula. So both the conductors are now carrying currents, I1 and I2. They are both infinitely long. There is a distance between them, which in this diagram is given as R. And that's the formula. And that's the formula for force on each meter, because you're dividing it by the length. So that's the force on each meter. Mu naught by 2 pi. I1, I2. That's an incomplete formula. Wait. That's an incomplete formula. Can you correct it? Yeah. Divided by. Yep. It'd be wonderful if you can understand how we get the equations, if you can take time for that. And this is the method using which the ampere is defined. So do look at the definition of an ampere. In that definition, you make I1 and I2 1. You make this 1, right? 1 meter. Make this also 1 meter. And then you would get, what's the value of mu naught? 4 pi times 10 to the negative 7. The 4 pi and 2 pi gets cancelled. That's how you end up with 2 times 10 to the negative 7 newtons per meter. Look it up. That's the definition of an ampere. Magnetic field of a current loop. This one we did using Biot and Savart's law. So you have a loop carrying current. If it's a single turn, that's when you call it a loop, obviously. And I'm writing the formula for magnetic field right at the center, not the magnetic field at any point on the axis. So the magnetic field at the center of the loop is mu naught I by 2R. If it has n turns, then you got to multiply it with the number of turns. So that formula is important too. So make sure you have this on the formula sheet that you make. So that's the formula for magnetic field at the center of the loop. And that is when it's a coil having n turns. Ampere's law. And you have to actually know what it means. So if you have a conductor, you imagine a closed path around it, and then you take the line integral of the magnetic field with the length as shown, and then you should get mu naught times I. But what's I? I know it's the current, but be specific. What's I? Is the current inside that loop. So if you have a current here, In another conductor, you will not be considering that because your loop is here. See? It depends on how you take the loop. So remember, or just write I enclosed here. I'll make it clearer. I enclosed means that's the current inside the loop. So that's Ampere's law. Making way for a conceptual question. And obviously, that's a dot product. You know what that means? When you take a dot product, it's going to be cosine theta that comes in, right? Which means when theta is 90, it vanishes. The dot product vanishes because cosine 90 is 0. Are you with me? Yeah, so keep all that in mind when you write this. And then you have the magnetic field of a solenoid, very important, a solenoid, and that is the magnetic field of a solenoid at any point on its axis. And this is where we use the Ampere's law. We considered the closed path here, okay? And we found out that B is mu naught Ni, but be careful about the N. Does anybody remember what that is? Whenever capital letter is used for N, it's the total number of turns. But when a small letter is used, it's the number of turns in 1 meter. That's very important there. So that's not the total number of turns. That's the number of turns in 1 meter of the solenoid. So don't make a mistake there. So if I give you the total number of turns and the total length, please divide, find the number of turns in 1 meter and use it. That way you won't miss that grade. I'm specifically writing that. N is the number of turns in 1 meter of the solenoid. Of a toroid, I think, next. Magnetic field of a toroid. Again, using Ampere's law. Let me ask you this. What's the magnetic field inside the toroid here? What's the magnetic field here? Let's see how much you remember. 0. And outside is also 0, right? So the only place where you have the magnetic field is right within the toroid. Nothing inside it, nothing outside it. And the formula for what's inside is now this. So look at the difference. Caps N, what does that mean? That's the total number of turns. Total number of turns. R is the radius. Radius of the toroid. When I say radius of the toroid, you should understand, I thought you would ask me, is it the inner radius or the outer radius? You know, that's confusing. So R is actually the radius of the path that you're considering. You see this path? So in this case, it would be the radius of that loop. So R could vary between the inner radius and the outer radius. Okay, that makes it clear. Could be anything between the inner and the outer radius. Then we come to self-inductance. Self-inductance is basically defined this way, one of the formulas. This is the self-inductance. So the induced EMF is negative of the self-inductance times the rate of change of current. What is the unit of inductance? Henry. Okay. And then the self-inductance of a solenoid. Self-inductance of a solenoid is mu naught n squared A by length. Don't get confused between these two. That's the self-inductance, that's the length of the solenoid. A is the area of cross-section. N is again total number of turns. Mutual inductance. Now, mutual inductance is defined as in the same format. It's exactly the same. But remember, this is the rate of change of current in a neighboring coil, right? And this is the induced. So this would be the rate of change of current in a primary, and this is the induced EMF in the secondary. So in mutual inductance, you're always talking about two coils, aren't you? You have a primary and a secondary. And then if you have a coil with a secondary winding, the formula for mutual inductance is mu naught N1 N2 A by the length, where L is the length. That is the formula. Now you know N1 is the number of turns in the primary, N2 is the number of turns in the secondary. And A is the area of cross-section of the primary. Usually they will almost have the same area because the secondary is wound on top of the primary. Because you want it very close to the primary, right? But in case there is a doubt, A is the area of cross-section of the primary. Moving on. Energy of an inductor, 1/2 Li squared or Li naught squared, where I naught is the maximum current through the inductor. And this is how we derive it. Energy is always connected to work, right? Work is integral P dt. This is the second time I'm writing that. And power is, electrical power is the product of voltage and current, right? So, power is the product of voltage and current. And then I've substituted power is E times I, and then E is L di by dt, if you remember. And then the dt's get cancelled, and integral Li di, I forgot to write I there. No, I is di by dt, right? Yeah. Integral di is, that's how you get it. Wait. All right, so it's actually IDI and then. So that's a formula for energy of an inductor. LRC, 10 point, maybe. Inductive reactance. Inductive reactance is given by this formula. Inductive reactance depends on the frequency directly. So as the frequency goes up, the inductive reactance goes up. But the capacitive reactance is inversely proportional. So you can see the frequencies in the denominator. And then impedance is actually the net of the resistance and the reactance is given by this formula. And then you have the phasor diagram. Remember that the voltage across the inductance leads the current by 90, across the capacitance lags. You remember all that? And the resistance is in phase. So this is the resultant of the inductance and the capacitance. Oh, I just left it as Excel. Oh yeah, I'm coming back. And just try to remind you about, you remember this? EMF leads the current by 90 in an inductor. Current leads the EMF by 90 in a capacitor. And then you get this phasor diagram. And the formula for tan theta is, of course, XL minus XC by R. And the resonant frequency is given by 1 by 2 pi square root LC. And at resonance, these two become equal to each other, so at resonance, the impedance becomes equal to the resistance, doesn't it? Okay. So I saw that you're all good at this, so I said, okay, one more chance, and then you get the 10 points again. And the maximum current then at resonance is EM by R. You know the relation between RMS and peak? RMS is always peak divided by root 2. So if you want the RMS current, then divide the RMS voltage by R. If you want the peak current, divide the peak voltage by R. Simple. Okay. And if nothing is mentioned about a certain voltage in a problem, it's always the RMS. So if nothing is mentioned, so let's say in a problem you have 120 volt, blah, blah. That 120 volt is the RMS voltage. So by default, what's given is always the RMS voltage. Note that down. Many times I give it, right? Like I tell you it's the RMS, but I need not. By default, it's always the RMS. Like if it's the peak, it'll be mentioned. Okay. Diffraction, just did, right? Diffraction at a single slit. Now, this is where the formulas become opposite, kind of, remember? Diffraction at a single slit. Condition for brightness and darkness. Now, so, just wanted to remind you about that. Condition for minimum now, or darkness, is d sine theta is equal to m lambda. I just made a quick sketch of that to show you what the terms stand for. In this case, it's the width of the slit. Y is the distance of the point from the center. And that's the distance of the slit from the screen. And tan theta is y by the distance. So you have to be careful here. You cannot interchange. One is sine theta, the other is tan theta. So when you work out problems, you have to actually use this formula, find theta, and then plug it back into this. Diffraction, grating. This is the only formula you need, but you need to know what the terms stand for. This is called the grating law. What's N? See, here don't go total number of turns. I know it's the number of turns, number of slits. I'm saying turns. Oh my goodness, number of slits in 1 meter. Yeah, that's the number of slits in 1 meter, and it's given by 1 by d, where little d is the width of one slit. The width of one slit, which is incredibly small. That's the grating law. Resolving power. Resolving power. Now, this is not resolving power. This is called the limit of resolution. Remember this? The angle, the smallest angle that can be resolved by a telescope is given by this formula. We're talking about a telescope here. So what is caps D if it's a telescope? What's caps D? The diameter of the aperture. Okay, and the 1.22 comes in because it's a circular slit, right? Circular aperture. Lambda is the wavelength, of course. Remember that resolving power is inversely proportional to this. So if theta is small, that means the resolving power is big. Obviously, theta is in radians when you have that formula, not in degrees. So that's what you mean by resolving power, which is the white screen. Thank you.